Hi, this is Maria, and today we're going to talk more about atomic theory throughout the centuries. We're going to start with the cathode ray tube experiment and gold foil experiment, and then we'll end with emission spectra. So our goals for this video are really for you to learn more about the details of each of these experiments and to see how each experiment really changed our picture of the atom. Becky and I really want you to understand that our picture of the atom has changed dramatically over time. As more and more information has been gained through experiments, we've really been able to understand that the atom itself is far more complex than originally pictured. So if you remember, Dalton had proposed the solid sphere model, where atoms were represented really just by a sphere, and it was not able to be divided any further. That was it. So about 100 years later, J.J. Thomson is looking at these cathode rays. Now, what cathode rays are is using a tube full of gas. If you put an electric current through that tube of gas, you'll end up seeing that it glows. Well, J.J. Thomson ends up setting up this really neat experiment where he takes a cathode and anode plates, so negatively and positively charged plates, and is able to shape that glowing substance inside the tube into a beam. Now, he does that by forcing it through this plate here, where you see there's this little hole at the end. And he's also able to track because there's this phosphor coating on the back, and that phosphor coating will glow when the beam hits it itself. So this is what his setup is. Now, J.J. Thomson clearly had to have the suspicion that the atom was in fact divisible and that perhaps there was some charged particles in it, because his setup ends up looking like this. Now you'll see here there's the positive and negatively charged metal plates that are added that are now over here. When he runs this experiment, he ends up seeing that the cathode rays end up curving towards the positive plate and away from the negative plate. Now, if you remember, positive attracts negative, so this is already implying that ray is negatively charged. So with this is now telling us, in fact, the atom is divisible, and since it's divisible, what he ends up proposing is called the plum pudding model. Now, since he knows the atom is neutrally charged overall, but now he knows there's these new small negative particles, he ends up saying that there's a positively charged background, and that positively charged background has these small negative particles embedded into it, and he calls them electrons. People call it the plum pudding model, but I'm sure not a lot of you eat plum pudding anymore. You'll hear it referred to now as the chocolate chip cookie model, where you would imagine that the chocolate chips are electrons, and where the cookie itself is representing the positively charged background. So, just a few years later, one of J.J. Thomson's students, Ernest Rutherford, ends up performing perhaps my favorite experiment of all time, the gold foil experiment. Now, in 1909, so just a few years later, he ends up using these alpha particles. And before I tell you what the gold foil experiment is, I want to tell you what an alpha particle is. An alpha particle is usually represented in diagrams with this alpha symbol. You've probably seen it before. And alpha particles themselves are fairly large, and they're positively charged. Those are the two things that you really need to know about it. You really don't need to know anything else. So now I can describe the experimental setup. He's got this fluorescent screen, which is represented in green here, and he's got this really, really thin piece of gold foil. He also has a radiation source, so what's emitting those alpha particles, and that's shooting it straight at the gold foil. Now, what he would expect is that those alpha particles would just go directly back. That's it. And that's what he sees for the most part. Almost all of those particles end up going through and they hit the back of the screen. But some of them end up slightly deflecting. Some of them just do a small deflection, and some of them almost are shot back towards the radiation source itself. Now, it's not a lot of them. It's just a few that end up doing this deflection or even this extreme deflection. But what it tells us is, well, the Thomson model really cannot be right. We would have expected that it goes straight through. That's really it. That's what we would have imagined. But those particles that slightly deflected, Well, since we know that alpha particles are positively charged, that slight deflection suggests that maybe it's just another slightly positive uh, particle that's acting on the alpha particles themselves. And so then we see things like this, where there's that small, tiny deflection. But there's the ones that shoot sharply back towards the detector. And those we would expect they probably hit some sort of large mass. And since this is what Rutherford ends up seeing, he ends up producing a new model of the atom itself. This is also referred to sometimes as the planetary model of the atom, but we might just call it the Rutherford model of the atom. There's a positively charged nucleus in the center that ends up containing most of the mass of the atom itself. And that positively charged nucleus is why there was those deflections when seeing this particular, in seeing those results. There are electrons and they orbit around the nucleus, but there's no defined path. And that's important because we're going to go into our next experiments. Bohr, who ends up just a few years later, ends up coming up with this new model. Now, where Bohr ends up coming up with this new model and why he knew that the Rutherford model couldn't be true was because he knew that as a charged particle moves in a circle, they knew that it would lose energy, which should cause the electron to crash into the nucleus. But there's no evidence of that occurring at all. So the Rutherford model must be wrong. So he ends up coming up with this idea that electrons travel in these very definite orbits, and that electrons emit specific frequencies when going from one orbit to another. So that's a little complicated, and this is more just of an idea, but he ends up going through and he ends up actually calculating for the hydrogen atom what those specific frequencies should be. Does it work? You bet. Bohr calculates these frequencies that should be seen for possible transitions in the hydrogen atoms, and it matches perfectly. But it only actually works for the hydrogen atom. However, this is such an important idea that even though there's some definite flaws in this particular model, he ends up getting the Nobel Prize, even though it only worked for the hydrogen atom. All the other elements, not so much, but did work for the hydrogen atom. Another big problem with this particular idea is that it essentially states that electrons are always going to be the same distance from the nucleus. Electrons are not always the same distance from the nucleus, and scientists knew that at the time. And so that's why we've modified this particular model more from when Bohr came up with this idea. However, it's a really, really useful idea, and we'll talk about atoms a lot in this class, referencing this picture that you see here. So for the Bohr model itself, we know electrons are found in distinct energy levels. There's only so many electrons that can go into each energy level. When electrons are in their lowest possible energy levels, they're referred to as ground state electrons. Now, excited electrons, so if some energy is introduced to the system, an electron can be excited from its ground state into a higher energy level. So for example, if we were saying that this is the hydrogen atom, you would expect that normally the electron would be in its ground state in the first energy level. But if it's hit with enough energy, then it could possibly go maybe to the second energy level or the third energy level. But when it goes up to these higher energy levels, it's called an excited electron. It's not going to stay there for very long. So it will end up releasing its energy, usually as a form of light or infrared radiation, and it will end up returning to its ground state itself. This is going to be very important for your first lab. So I want you to make sure that you ask whoever your teacher is more questions about this particular model. So here's your question for the next class. What would have happened in that gold foil experiment if alpha particles were actually negatively charged instead of positively charged in the gold foil experiment? Just write down some ideas. You do not have to be correct or right. We just want you to think about it, and we'll have a discussion the next time that we see you in class. All right, thank you for listening, and have a good night.